Welcome to what I believe is our last unit in nuclear chemistry. This is kind of a basic view, summary of the applications of radioisotopes, the dangers posed by radioisotopes as well. This is in the form of a reading, but I'm just going to give you this in the form of notes. You can then read the actual text and see where my answers come from. Let's get into it. What materials can carbon-14 be used to date? Well, remember, we are made of carbon, so it makes sense that previously living material can be dated by carbon-14. I want to give you a little bit more background about why this is. As we said in a previous lesson, carbon-14 is continually made in the upper atmosphere, and so it maintains a certain level, a certain concentration. That carbon-14 gets incorporated into carbon dioxide, which of course is absorbed by green things on the surface of the Earth. So the carbon-14 gets from the upper atmosphere into leaves on the surface, and then let's say here's Carl the herbivore. Carl eats up all of these plants, and so because he's eating plants with a certain constant level of carbon-14, Carl's carbon-14 level remains constant for his life. But then, of course, one day there's an accident, and Carl the herbivore is no more. And at that point, the amount of carbon-14 is fixed in his body, and for hundreds or thousands of years, through decay, this amount drops. It drops by half, by 75%, and then, therefore, we can use the remaining amount of carbon-14 compared to what it would be if Carl was alive, and we figure out when Carl was alive because we know what the half-life of carbon-14 is. Rest in peace, Carl. And of course that dovetails with number 2. Why does the amount of carbon-14 in organic material decrease over time? Well, very simply due to half-life decay. In the case of Carl the herbivore, when he passes away, the amount is fixed, and what was originally 100% gets cut in half, and that's over 5,715 years. And every time it's cut in half, we know that 5,715 years has passed. Number 3, why can we detect the presence of a tracer like carbon-14? Well, this is another use of carbon-14. It turns out if you just have carbon-14 in your organism, it's not only going to break down, well, breaks down, and of course when it breaks down we know it gives off beta particles, but beyond that it gives off the very, very penetrating gamma rays. All decays give off gamma rays, and gamma rays can be detected externally. I've already made a couple of drawings. Number 4, what radioisotope is used to detect and treat thyroid disorders? Well, here I've sketched thyroid glands are in the neck, and it turns out that thyroid glands are designed, so to speak, to absorb large amounts of iodine. Well, if they're going to absorb iodine, then they're certainly going to also absorb a radioactive form of iodine. And as a result of that, these are going to cause these to glow. It'll obviously release gamma radiation, which is detectable. And also the iodine radioisotope, by the very fact it's releasing radiation, can be used to kill any cancerous cells in the thyroid area. Of course, it kills healthy cells too, but because of their out-of-control way of dividing, the cancer cells are far more vulnerable to death by radiation. Number 5, why must the half-lives of medicinal radioisotopes be short? Well, we just mentioned iodine-131 is used to treat thyroid disorders. It turns out its half-life is only on the order of days, meaning if you get past a month, you have very, very little left because all of it has been cut in half in about 8 days, and another 8 days, a quarter's left, an eighth is left after another 8 days, after about a month, 16th, and pretty soon we have precious little left. And that's important because if the iodine remains in your body, you want it to decay quickly. If it stays in your body for a long time, it's going to be, for the rest of your life, bombarding healthy cells with radiation. So again, it's to minimize the exposure of healthy tissue to radiation. Let me write that. to minimize the exposure of healthy cells to radiation. Of course, some healthy cells always are killed in the process. Number 6, why is uranium-238 suitable for dating objects such as rocks? Well, keep in mind, rocks are extremely old. If you try to, let's say there was carbon in rocks, there's really not, you couldn't use carbon-14 to date them because the half-life of carbon-14 is very short. It's only on the order of about, let's say, 5,000 years. Well, by the time you get to the point where only a little bit is left, not much time has passed. By the time you get to the point where maybe you only have 1/64th of the original, or 1/128th or beyond, 1, 2, 3, 4, 5, 6, 7, maybe 35,000 years have passed. You get to the point where it's not detectable anymore. Well, you need something that is going to be sticking around for the long term. You need radioisotopes that have extremely long half-lives, like uranium. Let me put it to you this way. The half-life of a radioisotope should be comparable to the age of the object being dated. So, if the object, in this case, are rocks are hundreds of millions, billions of years old. Therefore, you really do need a radioisotope like uranium-238 with a half-life of 4.47 times 10 to the 9th years, which is about 4.5 billion years. What dangers does radiation pose to people? Well, I wrote it already. There's damage to cells and to tissues. So it can actually, lead to the death by killing healthy cells and tissues. It can also cause cancers, which of course are very nasty things, very difficult to treat, and sometimes the cure is almost as bad as the disease. They actually can even damage your DNA, your genetic material, and give rise to things called mutations. So it can be pretty nasty to people, so we want to always minimize our exposure to radiation. Number 8, how is cobalt-60 used to keep food from spoiling? Well, as it said in the reading, cobalt-60, as it decays, releases gamma radiation. There's a process called irradiation, meaning if you're going to ship, let's say, produce, lettuce, tomatoes, over long distances, there's the possibility for bacteria to develop. And the bacteria, besides damaging the integrity of the vegetable, can actually go and hurt people then. But in case of just spoiling, the benefit is that the gamma rays are going to kill those bacteria before they can help the food to spoil. It's really that easy. It's a very prominent practice. Number 9, why must radioactive waste be stored for hundreds of years? Well, in short, it's to ensure the radioisotope decays sufficiently, meaning to a point where there's so little of them that they no longer pose any sort of hazard to living things. I want to give strontium-90, a typical product of nuclear fission. Notice that the half-life of strontium-90 is 29.1 years, a pretty long time. Now, let's say we wanted to get it to decay so that only 1/1000th of the original amount remained. In other words, extremely little. At that point, it probably poses very little danger. Well, in that case, that requires 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decay events. So half-life times decay events will give you the amount of time. So it would take exactly 291 years to get to that exact fraction in which it's really no longer that dangerous to human beings. So hence, we need to store them safely for a very long period of time. Number 10 is sort of a repeat, but it's a good contrast question. Both carbon-14 and uranium-238 are used for dating. Explain why these radioisotopes are used to estimate the age of different sorts of things. Remember what I wrote up top, that the half-life of a given radioisotope must be comparable to the age of the object it's trying to date. So since the half-life of carbon-14 is on the order of thousands of years, that means it should be used for dating something that is old up to thousands of years. Maybe carbon-14 could be used to date things that are about 50,000 years old, beyond which time you don't really have much of it left. Whereas uranium-238, which is 4.47 billion years. That's on the order of geological time. The Earth itself is estimated to be about 4.5 billion years old, so that means over the course of the Earth's lifetime, the uranium-238 that there was, or let's put it this way, of the uranium-238 that there was, there's only about half of the original remaining due to decay. So again, the half-life of a given radioisotope must be comparable to the age of the phenomena you wish to date. Turns out number 11 and 12 are repeats, so in their place, I want to put something that's not in the article. The benefit of nuclear power versus the danger of nuclear power. Again, as I say, as educated citizens, future citizens, well, you're citizens now, but as educated adults in the future making decisions as citizens, you're going to have to tackle, you have to grapple with these things. Well, the benefit of nuclear power is that we get to replace, it's one way, perhaps it's a bridge measure of replacing fossil fuels. Remember, the problem of fossil fuels is that they endlessly pump carbon dioxide into the atmosphere. The benefit of nuclear power would be you can generate energy without generating any greenhouse gases. By contrast, I think you already know the danger. The problem of nuclear power plants, is the very same problem that the world first experienced when nuclear bombs, or I should say atomic bombs, were exploded. They produced lots and lots of radioactive waste. That radioactive waste is dangerous to human beings, animals, and so on. So it's the problem, we're not releasing it directly into the environment, unless there's an accident, although we should write that. An accident involving a nuclear power plant can accidentally release radioisotopes into the atmosphere, or storage. Now, storage, if it were perfect, would not be a problem, but we also have the problem that accidents will happen even in storage. And the same story could happen. For example, let's say you bury your waste, but it turns out your waste happens to be near an aquifer, meaning a source of underground water. Well, if uranium, the byproducts of something like strontium-90 were to leak into the water table, well, that water table is contaminated for a very, 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 very long time. And because human beings rely on different water sources. All right, I think that covers it. That was the unit. Please rewatch all of these units prior to quizzes or tests on this, and I hope you found them helpful. Bye-bye.